Hello and good day to you. Come, pull up a chair as we venture into exploring the fascinating subject of MONET, Mixture of Monosemantic Experts for Transformers. This noteworthy advancement emerges from the collaborative efforts of researchers at Korea University, KAIST, and AIGEN Sciences. Today, we'll embark on a journey into the intricate workings of large language models, particularly focusing on how MONET offers a fresh perspective on understanding these complex systems. As these models grow in scale and capability, deciphering their internal computations, what we refer to as mechanistic interpretability, becomes increasingly vital. One significant challenge in this area is the phenomenon of polysemanticity. Now, that's a substantial term, but it simply means that individual neurons within a neural network respond to multiple, often unrelated concepts simultaneously. Think of it like a single radio station broadcasting several different shows at once. It becomes quite a task to tune in to the one you're interested in. This overlap makes it difficult to interpret what each part of the model is doing, hindering our ability to align these models with human values and expectations. Previous efforts to address polysemanticity involved techniques like sparse autoencoders, SAEs. SAEs attempt to disentangle overlapping features by learning sparse representations. Basically, they try to represent data using as few active components as possible. However, these methods often rely on something called post hoc reconstruction loss, where the model tries to reconstruct its input data after processing. This reliance can compromise the performance of large language models, making them less effective in their primary tasks. This is where MONET steps in. MONET stands for Mixture of Monosemantic Experts for Transformers. It incorporates sparse dictionary learning directly into the end-to-end training of the model using a Sparse Mixture-of-Experts SMoE architecture. Let's unpack that a bit. In MONET, the model is composed of a vast number of specialized units called experts. Each expert is monosemantic, meaning it focuses on a single concept or feature. In this architecture, there are an astounding 262,144 experts in every layer of the model. You might be pondering how it's possible to manage such a multitude of experts without running into computational roadblocks. MONET introduces a novel expert decomposition method that allows the total number of parameters, the adjustable elements of the model, to scale proportionally to the square root of the number of experts. This ingenious approach mitigates memory constraints and computational demands, enabling the model to scale up experts significantly without becoming unwieldy. By having a large number of specialized experts, MONET achieves mutual exclusivity of knowledge among them. Each expert is responsible for a distinct piece of information, akin to having a team of specialists where each member excels in their own field without overlap. This structure enhances mechanistic interpretability because we can observe which experts are activated for specific inputs, providing transparent insights into the model's internal processes. The researchers conducted several analyses to demonstrate MONET's capabilities. One such analysis involved domain masking. Utilizing the MMLU Pro benchmark, which categorizes question and answer sets into 14 distinct domains, they identified experts that specialized in particular domains by examining the routing probabilities, the likelihood that a given expert is activated for certain inputs. If an expert had a significantly higher routing probability for one domain compared to others, It was considered specialized in that domain. By selectively removing these domain-specific experts, they could observe the impact on the model's performance across all domains. This selective unlearning allowed them to manipulate the model's knowledge in precise ways without degrading its overall functionality, a compelling demonstration of controlled knowledge manipulation. In another experiment, the team explored multilingual masking. They identified experts associated with specific programming languages by analyzing the skewness in routing probabilities. By adjusting or removing these language-specific experts, they effectively enabled the model to unlearn certain programming languages. This manipulation did not adversely affect the model's general performance, showcasing MONET's ability to tailor its knowledge base selectively. Perhaps most importantly, the researchers addressed the critical issue of toxic content generation. They identified experts correlated with toxic outputs by calculating the Pearson correlation coefficient between toxicity scores and routing probabilities. By purging these toxic experts from the model, a process they termed toxic expert purging, they fundamentally adjusted the model's behavior to produce safer language generation. This adjustment was achieved without compromising the model's effectiveness in other areas, highlighting MONET's potential for promoting ethical AI practices. In summary, MONET presents a parameter-efficient architecture that significantly enhances mechanistic interpretability in large language models. By integrating sparse dictionary learning directly into model training and employing a vast number of monosemantic experts, MONET overcomes the limitations of previous methods like SAEs. Its novel expert decomposition method allows for the scalable expansion of experts while keeping computational demands in check. This architecture facilitates transparent observation of the model's internal workings and enables robust manipulation of knowledge across various domains, languages, and in mitigating undesirable content such as toxicity. The ability to adjust the model's knowledge base without degrading performance opens up new possibilities for creating AI systems that are both powerful and aligned with human values. Thank you for joining me on this exploration of MONET and its contributions to the field of artificial intelligence. It's an exciting development that brings us closer to transparent, controllable, and ethical AI systems. As we continue to push the boundaries of what's possible, approaches like MONET offer valuable pathways for ensuring that our technologies serve us in the most constructive ways. Until our next intellectual adventure, stay curious and keep questioning.